Thank you both for putting the session together and for the invitation to present. So I will be presenting a project that we had that took quite a bit to put together, and it's mainly experimental, and these are tests that we did right after the lab opened after the pandemic. So that's a lot of people to help about this. That's probably the longest acknowledgement slide I've ever put. Lots of students, but also we worked together with 5 GEON at that time, New York State DOT that funded our project, and also the contractor that was in charge of replacing a couple of beams around campus, and also a company that helped, Erdman Anthony, that helped plan the whole thing. So because we needed some of the requirements about the beam extraction transportation to go into the contract for the replacement of the beam. So this is an outline. This is the presentation. The bridge right before it was replaced. This is by the campus at UB. So less than a mile from our lab. The beam was not doing well, at least from that's what they got from the inspections. The outside girders were in bad shape. And that's what caused them that brought up the decision to replace the beams about 35 years after they were constructed. So it's a little bit early for what they wanted, but once I found out about this, I went to DOT and I asked, okay, what can we do with the girders? What would you be interested in? And the interest there was to work on some strengthening methods. So we worked, we did some literature review, talked with Scott and his group at 5, and then we decided what we wanted to do. So that would be FRP anchorage. So this is the cross section. These are all box girders, so we don't have the ability to go and put U anchors. That's not an option here. So we would, and this also quite thin. So the concrete cover here was about, from what I remember, 4 or 5 inches for the box beam. So, and the DOT wanted us to increase the flexural capacity by about 30%, make sure we avoid shear failures, and also apply a methodology that could be applied in the field. So we were kind of limited into what we would do, so that it's something that can be done in the field. These are the beams that we picked. So these are the approach spans. They're about 60 feet long. And we had, for whatever reason, in the design, they had one line that was 3 feet wide and everything else was 4 feet. So we ended up getting the 2 opposite beams that were 3 feet wide, and then we got also an adjacent one that was 4 feet and had similar level of deterioration. This is from the field. There were some pins that were cast in place when they placed the beam, so we had to very carefully go and convince the contractor to get the core driller to drill the cores so that we could get the beams out of the bridge in as good as condition as we could. We had to store them temporarily there. That was COVID times, and there were quite a bit of logistics involved, and then we had to make the decision about what we wanted to investigate and what we wanted to do. So we got 3 beams. We couldn't have a control specimen as we would have liked. It was too precious for that. We did do some service load tests for every beam to check initial stiffness, check to see how they're doing under service loads. I'm not talking about any of this. This was on the unretrofitted beams, just to get a common denominator to assess their behavior. So once we decided what we wanted to do with the retrofit, we had to pick, obviously, material, thicknesses, widths, lengths, and the main challenge was the anchors. So we couldn't go, at least initially we were worried to go in the hollow sections. We had to shoot at the ends where it was a solid section. We went 5 inches deep, 45 angles. Then we had to decide about the fans and how many we would put them. And this was the layout for the first beam. Talking to Five, we said what would be the thickest that can be done in the field. They told us that would be 3 layers. We had 3 layers in the middle, 2 layers at the ends, and this is how the anchors went. Very similar to what was presented before. We had a low anchor to laminate ratio, and this would be the sequence process. So this mostly done by students, the prep work, drilling of the holes for the anchors. That was Sina, postdoc, who did most of the work. And then this is the application of the FRP. Here we're drilling the holes on the first laminate so we can pull the anchors through. And here's the end product. As you might have noticed, I mean, my background, the lab's background is all about seismic, so all lateral loads. We don't have the ability to apply vertical loads, so we had to switch things around a little bit. Here's about a minute long video about the whole process. It's quite a big beam, quite a bit of space in the lab, and again, we had a big crew working around it, so rotate it again. So gravity worked for us during the application. It was too scary to have to elevate and have students work underneath. Not the most safe setup, so the lab talked us out of it. So that's an asterisk into what we've done. So here we're patching some dents that or beam got during the transportation. Drilling the anchors. And that's how we apply the FRP. Lay it out, soak it, roll it back again. And again, we were told by a crew that came to teach us how to do it, so that should be the form in the field. We didn't have the tool that Five or other companies would use to soak the FRP, but we had to use the beam for that. Layout, we designed some supports. So these are the actuators, 4-point bending test. And this is what how this looks like. Obviously, we put quite a few strain gauges, displacement transducers. This is what we're getting from service level tests. And we did that also after we applied the FRP to see if we gained any stiffness, not much to see over here. Again, going back to section analysis, trying to see if what we know holds. It seems to it does. It's neutral axis moved a little bit, but nothing major. And here we come to the first test. So here we saw some delamination. And eventually we got that to fail. So going back, after the test, you see that we actually pulled the cover out with the FRP. We pulled, here are the anchors. So the anchors were pulled out. These are 5 inches inside that whole solid section. So we were able to get them out with the FRP. And again, this was our 3-layer FRP. You see here the load displacement curve. The dotted red line is what we got as the bare beam capacity after everything was failed. So we were able to increase the strength quite a bit, and that gave us confidence, and went back to the drawing board to see what we wanted to do with the next beam. So having achieved the minimum that DOT required, we thought, okay, how about we reduce the layers to 2, so let's see what happens. Because we realized from the strains that we're not really using the fibers to their capacity. So that kind of bothered us, or we wanted to investigate how we can do to, and also get more from the anchors instead of failing the concrete. because of the thick laminate. So we reduced the thickness of the laminate, and on one side we got a little bit adventurous. We started moving anchors around to see if that would make any difference. So you see, we kept the same number of anchors, or ratio went up. Here's the second beam, how it failed. Not showing? Oh, okay. So here the lamination started here. It does not have to do with the anchor layout. We did have an anchor. Oh, sorry, this. I forgot to have the slow motion of this. It was a little bit scary to be up there. I will admit that. I was on a cherry picker to take this video. So, yep, that's how it did. So, so you can see that the failure propagated on one end. The anchors were not symmetric at this point, so we had lack of symmetry. And we realized that after the fact that one of the anchors on that end was not really installed. So something went wrong. So we had one anchor less, and the anchors were not at the two layers. We tried to be three, but it didn't work that well. So So throughout the length of the beam, we got a mix of pulling the cover out and just delaminating, and pulling the anchors out. So some anchors sheared, and a few got pulled out. So strength-wise, we actually did quite well. So you see that we got more ductility out of it, and a little bit more strength, which is kind of the opposite of what we saw in the previous presentation, where the thicker layer gave more strength. Here we saw that as we reduce the thickness, we increase the strength. I think it has to do with how much of the failure mechanism that we change, how much of the FRP we got activated. So we went back we had one more beam to design. So we went quite adventurous here. We really wanted to push the anchors even more. So we thought that, okay, let's reduce the layer to one. We had to make some adjustments. This was our 4 feet wide beam. We're out of the 3 feet ones. So we had to make some adjustments, but we kept everything proportional. So we used scaling law to adjust the width, but we kept the same number of anchors. So again, you see 7 anchors, and now they're all together. We're not going to the end. We're going to the hollow section of the beam, but we keep the symmetry. And we have one layer, so the rolls we got were not wide enough, so that's why you saw some patching and some cutting thinner, more narrow layers. Anchor to laminate ratio went up because, again, we're always keeping the same number of anchors. I mean, there's so many things that we would like to investigate. We just didn't have enough beams to check all these things. So this is even scarier than the one before. Yes, we did it. So we fractured the anchors. I mean, nobody got injured. I mean, we should have had it. So that was slow motion. So it looks good now. Again, it was a bit scary. But I think we were successful. We got what we wanted. So we really wanted to push the anchors. We did. So we have all the range of behavior that I think we could get out of 3 specimens. So there was a funny thing. There was a little strip that stayed there, never fractured. But jokes aside now, seriously, we really saw that we activated the entire concrete. We have uniform crack pattern, so that was quite successful for what we wanted to do. This is where the anchors are. So you can see that, so this I think I have another figure, yes. So you can see here the red and yellow stickers are where the anchors were located. We had to move one because we did hit some steel here, so, and the line with the chalk is, again, nothing high-tech, just tapping to see where we have delaminated FRP and where the FRP is holding. So you see that other than one anchor, essentially, all other anchors held in place. So, and that's why we managed to fracture. So, strength-wise, even more interesting, you see that we got a little bit more strength, but better ductility. So here's where FRP delaminated, here's where it fractured. So, and again, it went back to, so they all went back to the, what would be the strength of the undamaged beam. So you can see that, again, very contrary to what I would have expected before all this started and what we saw before. We did get, in terms of force displacement load, we got more strength and better ductility from this very messy failure pattern. So, trying to tabulate some of the results and compare. Again, there's not much specimens or as much as I would have liked, but even to get this done was quite challenging. So I think what's interesting to notice is that the capacity compared to the bare beam, that we went over 50%. So with that, we beat what our goal was, and we see that we got that with a thinner layer. Some information about strains. This is right before the peak, but right before the bonding, I'm sorry. So you see that we do get higher strains as we expect on the thin layer, and even after debonding, but before the failure, we see that we have activated a more uniform area, and this is all throughout the length of the strain gauges that we got. So the FRP capacity is best used obviously in beam 3. So we would like to do some numerical modeling. It turns out it's more challenging than I thought. We used Abacus, and for the last beam that anchors were not failing, actually this is very, very good. I was quite impressed. But model the failure of the anchors, we got stuck and we ran out of money. Postdoc needed to move on with his life and get a job, so that's where we stopped. There is a report submitted 2 years ago to DOT. It's still coming out. So, and that holds us from submitting papers. I think it's in the legal review now since August. Hopefully it will be out soon. So you can see the results, and thank you for your attention.